All right, so welcome everybody. So it's a pleasure to have today Mihai Păun, who will tell us about positivity of direct images and algebraicity of holomorphic foliations on compact Kaehler manifolds. Please go ahead.
Thank you very much for the invitation. It's a great honor and a great pleasure to see you online here. So as Mircea just announced, I will explain a few things about joint work with Julian Cao. So let's go ahead. So this is what you will see in the next few minutes. After a few words of introduction, I will where I present the main results. Then here you will see somehow one of the main technique in the proof that will come, and then the few facts about the pseudo effectivities of line bundles and of vector bundles. Finally, the algebraicity criteria and the statements, the outline of the proof for the main results. Okay, so let's go ahead with the statement of the main results. So X would be n-dimensional compact Kaehler manifold, and then a 1-1 class, real 1-1 class, it's always denoted by this with the brackets. And then for me, the cotangent bundle will be denoted just like that. As you see, it's Tx star, and then canonical with the Kx, top power of the canonical, of the cotangent, I'm sorry. And then, so in general, in this context, for a 1-1 class, not necessarily the first-chain class of a line bundle, this would be called pseudo-effective if it contains such an object, a closed positive current. So why is that, somehow, why that matches algebraic geometry is that if it happens that alpha is the first-chain class of some line bundle, Q-line bundle, then you can show that this is the same as L is the limit of effective Q divisors. Okay, so it's exactly that the notion that that you have in algebraic geometry. And then now this being said, let's see what one of the main goals of the lecture would be like this. So many people contributed to it, and then the version that I will present today is the one in my paper with Julian. Previously, for the projective manifolds, it was an article with Frédéric Campana a few years ago. So we have a compact Kaehler manifold such that the canonical is pseudo-effective. And then we look at the quotients of this space of holomorphic tensors. So we take m tensor power of the cotangent and look at the quotient of such an object. And then, so the point is that the determinant of any such quotients is a pseudo-effective line bundle. Okay, so somehow the positivity from the canonical is sufficient in order to have the same thing for the determinant of any quotient of the full cotangent bundle tensors here. Now, a few remarks about this sort of results. In the first place, it can be seen as a generalization of Miyaoka's semi-positivity theorem because, as you know, if the canonical is pseudo-effective, then the cotangent is generically semi-positive, so meaning that this result, when you restrict it, if X is projective and you restrict it as on a complete intersection, you will have the statement there. The difference between this and the Miyaoka's result, if you want, other than the context of compact Kaehler manifold, is that here we know that the determinant is positive when you couple to any Gauduchon metric. In classical case, only with Kaehler metric. So I will come back to this a bit later on. But anyway, so it's somehow a generalization of this result of Miyaoka comes from somewhere. Now, the proof, unfortunately, is rather indirect based on some results that we'll discuss next. And why I feel a little bit frustrated here is that there is no differential geometric argument. That is to say, even if we assume, let's be generous, let's say that the canonical is even ample, there is no metric proof. There is no metric on X such that, okay, the induced metric here will do the job, will give you some positivity for the determinant. Okay, so there's no direct, no differential geometric argument. And this is a problem for people who are interested in algebraic hyperbolicity, for example. Anyway, I'll not insist on this point, but it would be very useful to have such a proof precisely because of that connection with with Kobayashi hyperbolicity. And then another result that I'll present is the following. So we have a movable class, for example, the n-1 power of a Gauduchon metric. Now, a Gauduchon metric is simply a Hermitian metric on X, which is not necessarily Kaehler, but the n-1 power is DD bar closed. So it has some properties which allow you to measure the degree here. So now, if E is a coherent torsion-free sheaf, excuse me, then its slope with respect to this class makes sense, and then it's can be computed exactly like this. You first class of E, this is a well-defined one-man class on X. So you integrate against gamma, and then divide everything by the rank of the generic rank of E. Now, this is well defined precisely because of this condition here. C1 of E is determined modulo DD bar exact forms, and then they disappear when they couple them with gamma here. So we have a degree with respect to this metric. And then, as usual, we have the notion of minimal slope with respect to this movable class, which is the infimum of the slopes of the quotients of E, as usual in the stability theory. And then, so the result, which somehow was motivated by the very interesting progress by Wenkao Wu 1 year ago, is the following. Now, if we have a compact Kaehler manifold and a foliation for which this minimal slope is positive for some gamma in this group, so let's say for some Gauduchon metric, then the consequences are rather dramatic. That is to say, P is there exists a rational map for which the generic fiber is exactly the foliation, so the leaves they compactify, and then moreover these leaves are rationally connected. Now, maybe a few comments about this. So, like I just mentioned, in the case of the tangent, this is due to Wenkao Wu. Also, the fact that such a foliation is algebraic is due to him. And then the rational connectedness, you will see it in a second. So, yeah, so that's what I said. This result, uniruledness of arXiv, and canonical is not still effective, follows from the existence of such a structure. And then it settles a conjecture by Jean-Pierre long ago. And then, so now what are the main techniques involved in the proof? Well, there are two of them, the positivity of direct images and algebraicity criteria for foliations. Okay. So maybe so far, do you have any questions about this? So this is the two results I would like to present. So what you will see next is how the arguments are built. So if there is some notation, something you want me to say about it, doesn't seem to be the case. So let's move on. So in the first place, positivity of direct images. Now, this is a very elegant theory which somehow started at the same time from two important sources, like complex variables by the Japanese school from Nishino and Maitani Yamaguchi, and then from the algebraic side with important works of Griffiths, Fujita, and Five. Now, the version I will give you here was obtained by Bo Benson a few years ago. And so now his result starts like this. So we take a domain in the product of two Euclidean spaces. Now it's important to allow domains which have this property, but for the sake of this talk, let's say it's just a ball. And then we take a pluristychomorphic function on omega. So I will give an example of such functions in a second, make some comment about it. And then for t in this first set of variables, we look at the Bergman kernel of the slice omega t, so that is to say omega intersected with t times Cn, and with this weight. And then the statement is that the function log of this Bergman kernel is plurisubarmonic, that is to say, IDD bar of this function of the log of this of the Bergman kernel is positive. So here it's important to remark that we have this positivity with respect to both variables, t and z. So now a few words that appeared here, for example, this class of plurisubarmonic functions. So a nice example to keep in mind is constant times the log of the sum of holomorphic functions. So there is a connection with algebraic geometry, right? This class of functions is a plurisubarmonic. And then but it's slightly more flexible. For example, if you take the maximum of two such objects, you still stay in the same class. Okay, so you have this amount of flexibility, which allows you to do operations which are not allowed in general algebraic geometry if you just look at the sections line bound. So this is the sort of function, the sort of weight function which we have here. And then what is the Bergman kernel is simply the restriction to the diagonal. So it depends on two variables, z and usually w. And then what you do is to look at this space of holomorphic L2 functions here. This is a Hilbert space because we are in L2. And you just take an orthonormal basis, ON. Orthonormal basis of this one will give you the Bergman kernel. So if you want for t fixed, the Bergman kernel is simply the sum of the squares, absolute value squares of basis of this Hilbert space. Okay. So if you take any book in complex analysis, a good one, then you will learn that IDD bar of log of the sum of the squares is semi-positive. So it has this property here. But somehow the miracle that happens in this situation is that it's also this IDD bar of the log is also positive in the base direction, so to speak, with respect to t here. And then you see this is really very, very surprising because orthonormalization is an operation which is somehow very bad when it comes to holomorphicity, right? So something must happen. Something must happen there in order to keep this property here. And then if you want to have a look at the proof, this is really fantastic in the sense you see there the L2 estimates at their best, in the sense that there is estimate in the L2 estimates which has the constant 1. If that constant is 2, then the proof collapses. I mean, this really uses the fact that L2 estimates are very, very precise. Extremely nice. Anyway, so all those conditions here, the pseudo-convexity and then the plurisubarmonicity of the functions, they come into the picture to tell you that actually you get this convex or this plurisubarmonicity with respect to both variables, z and t. Okay, so now this result was further refined from domains in Euclidean spaces to Cn by many people, Benson and myself, and then Takayama, also Heiken, Papa and Schnell. So what is the situation here? Now let's assume that we have an algebraic fiber space. So we need some algebraicity involved in the proof, in this statement, I'm sorry. And we also have a line boundary over Y, which is pseudo-effective. That is to say, there is some metric for which the curvature is semi-positive. So this metric could be singular, but this condition has to be satisfied. So this means that for the local weights of the function, IDD bar is semi-positive in generalized sense. And then what you can do is to look at the L2 metric on the direct image. So this would be a torsion-free sheaf, but you can still. So if you remove some open, some Zariski closed subset in Y, codimension at least 2, then this is an honest vector bundle. And then the point is that if you do a similar construction as here, where the phi, the function here, is the role of this function is played by the metric of L, and then this base SYT is you look at the sections which are integrable with respect to this on each fiber. So again, you normalize them like this, and then the conclusion is that it's positively curved in the sense of Griffiths, which is more or less what I'm telling you here in the previous result. Okay. So this can be seen, if you want, as a global version of the initial result by Wu. Okay, so somehow the point is that within this framework, we have a very clearly defined object metric on this direct image, which has wonderful positivity properties from analytic point of view. Fine, and then maybe a few comments about these results. What I would like to say is, I mean, why do we need the projectivity of P? Because if we look at it, I'm giving you here as hypothesis something which has a close positive current inside, and I'm producing a metric here. This is positive in the sense of Griffiths. So, but then this is done through the space of sections, right? So because this metric is constructed by using the fiber sections. So the local projectivity of the map would be sufficient, and it's used in some approximation process. And then as a consequence, let's assume that the multiply ideal sheaf is simply the structural sheaf. And then this canonical of the fiber tensor with L is pseudo-effective. Then what you deduce is that you will have the same property for the relative canonical bundle twisted with L. So the relative canonical twisted with L will be pseudo-effective as well. Okay, so again, this is in the projective situation, if X is projective, or at least if the map P is locally projective. And then, so the question we are concerned with somehow is the Kaehler case, what we can do in the Kaehler setting, because then we cannot say that the pseudo-effective line boundaries are a limit of effective ones, right? We don't have the ample line boundary which allow us to do that. And then in this context, there is a problem which is still open, conjectured by Julian Zhao and Andreas Hörling. Now, let's assume that we have a holomorphic and surjective map between Kaehler manifold, compact Kaehler manifolds, and then a line boundary over the total space for which the curvature is semi-positive. And then again, if the multiply ideal sheaf is trivial, then here, I'm sorry, there's a kx over y plus L. Oh, no, sorry. So that the canonical plus L restricted to the fiber is still effective. That's still part of the hypothesis. Then the relative canonical bundle plus L is still effective. So basically the same statement is expected to hold, but this time for in the context of map between compact Kaehler manifolds. Now, so what is the main difficulty? Why is this still a conjecture? Well, because we don't have a natural candidate to fit in here. In the previous result, and in the projective setting, we have the sections of multiples of this plus some ample, and we play with those. Here, we don't have any ample line bounded around, so we don't have a natural candidate who would do the job here. But then there is a particular case which is somehow interesting, And then started with the work of Tsuji long ago, and then some remark of mine. So let's say that we have a 1-1 class which contains a smooth and semi-positive form, okay, semi-positive class. And then we assume that for each element generic y in y, then the canonical of the fiber plus the restriction of this class is scalar. That is to say, so as soon as you add the canonical, this class becomes scalar for y and y generic. And then the conclusion is that this one, the relative canonical plus beta contains a closed positive current. Okay, so if beta is a Fresnel class of a line bundle, then it's a consequence of, can be seen as a consequence of what I told you here. But then what is interesting here is that instead of using the space of sections, instead, in this context, it's the proof relies on Monge-Ampère theory. And then that's one of the very beautiful remarks, results by Hajime Tsuji, namely to say that for example, in this context, the Kaehler-Einstein metric can be seen as the limit of Bergman kernels. So somehow in the Tsuji case, which was beta equals to 0, he showed that the Kaehler-Einstein metrics have a plurisubarmonic variation. So somehow and he did this by approximating them with Bergman kernels. Okay, so even if I said to you that here there is no natural candidate, maybe there is, but we cannot work with him because here the hypothesis is that this class is scalar and our classes would be scalar but singular, so it will be so-called big classes, okay? And then the method of the proof somehow breaks down. Fine, but anyway, so let's keep this in mind, so that sometimes Monge-Ampère theory rescue us. We can get rid of the space of sections by working directly with special metrics. Now, another particular case would be the following. So in the setting above, that is to say, a map between compact Kaehler manifolds and so forth. Let's assume that we have a Kaehler metric on the total space together with a holomorphic 2 form such that this class is rational. Of course, this you can always find it if X is projective, X is scalar but non-projective by Kodaira. But then the additional hypothesis is that the restriction of sigma of this 2-0 form to the generic fiber of P is 0. Okay, so this is rational. But then when you restrict to the fiber, becomes positive and rational. So it's like you would have a fiber-wise ample line boundary. And then the conclusion follows. So that is to say, again, you know that the fiber-wise this is pseudo-effective, and then you get it for the global situation. Here for the relative canonical twisted with L, and minus the discriminant of the map. Okay, so this particular case would be relevant for the proof. Now let's see how this works, more or less. So that D of P is the discriminant of P. Just a few comments about the proof. So that, like I already mentioned, so this restriction to the fiber plays the role of an ample line boundary. But then why this statement is non-trivial is, of course, because the ample in question is only determined up to a topologically trivial line boundary. So you don't know that the objects that you construct, they will agree when you move from one fiber to another. But then, yeah, that's so what is happening is that you could imagine that you construct some metric, some representative here or above an open subset of Y, but then since this is not an honest line boundary over the whole family, it might not define a global object. But then why it nevertheless works is that, well, the story here is a bit longer than what I just say, but somehow the representative that we can construct by using this ample here will live in this class, for which you see no sigma, no. So we use sigma in order to construct this representative, but then in the end it doesn't show. Okay, so somehow the fact that a topologically trivial line bundle has zero curvature helps a lot. But anyway, so in this case, we can the somehow known techniques apply and then and give the expected result here. Fine, but so again, so there are two hypotheses. One, this magic omega and sigma, and then the second one is that the restriction of sigma to the fibers is zero. Okay, so now in the results I mentioned at the beginning, so there are some they concern the positivity of lines or vector bundles. So let's review some positivity criteria. First one is a very nice one due to Lamary, and then the proof is a very clever use of Han-Banach theorem. Tells you the following. So we have a 1-1 form, not even closed, doesn't have to be even closed on X, and then we know that the degree. So when we integrate over X alpha wedge omega to the power n-1. Well, the number that you get here is positive for any Godushon metric. So any Hermitian metric such that dd bar of this is 0, you know that this integral will be semi-positive. And then the conclusion is that alpha contains a positive representative, that is to say alpha plus idd bar of some function in L1 is semi-positive. Okay, for example, if alpha is the first Chern class of a line bundle, then if you're able to ensure that these integrals are positive, then automatically the line bundle in question is pseudo-effective. Okay, so that's a very nice result concerning the positivity for real 1-1 classes. Okay, so of course you have to make sure that this is true for any of those metrics. Now, that's the situation for line bundle. Now, in a higher rank, as always, it's a bit more complicating. The notion that one notion that will be important here is the following. So we have let's say a reflexive sheaf on X, and then we declare it pseudo-effective if I can construct for each epsilon positive a metric, eventually singular on this O of 1, restricted to the smooth loci here of the dual, such that the curvature is greater than minus epsilon omega y, and then this y here is a desingularization of this P of F star. So here, again, maybe this is always confusing. P of E for me is I'm looking at the lines, okay? So here, those are the lines in F star. Or if you prefer, the direct image of O of 1, it's exactly F, okay? So fine, so this is a rather liberal notion in the sense that sometimes people assume that this metric, you look at where it's singular, you don't want the singularities to project down to X, okay, from P of S star where it is. But then here we don't care about those. We are just happy with the existence of such an object for each positive epsilon. And then so the result I would like to mention here is very, very, very connected with great Griffith's conjecture, namely, so from positivity of O of 1, we want to extract positivity properties of F. Of course, like I said, this is far away. Maybe the one who started the show in this direction was Jean-Pierre de Mailly in 1994, then Christophe Morgan a little bit afterwards. And the version I represent here is due to Wenhao Wu. So we have a Kaehler manifold and a reflexive sheaf on X. And then we assume that this F is pseudo-effective. Then there is there is a subsheaf of f for which the slope is positive for any mobile class. In other words, the maximum slope is positive. Yeah, so it's not exactly the positivity of f, but somewhere inside we can detect some positive subsheaf. And then maybe it's instructive to see a little bit how the proof works. Just a few lines about it. Let's say that, let's ignore the singularities of f. Let's say that f is a vector bundle, and then the metric here, this is globally defined, not only on some Zariski open subset. And then for each m, let's consider the relative canonical bundle associated to O of this m plus r plus 1. R is the rank of E, twisted with multiple ideal shifts. So the r plus 1 here is meant to ensure that this is non-trivial. Okay, it's a simple result telling you that if you look at the projective space and you have some metric on O of 1, then this will be non-trivial if the rank here is if you twist enough, at least r plus 1. And then now for this we have some metric which is almost positive. This is like a minus epsilon here. So this one in the first place is a subsheaf of the symmetric power of m times the tensor of E, determinant of E. And then if we look at the curvature, what we know by the positivity of direct images that I explained, so this one will be bigger than some fixed constant times the metric on X. Okay, so the fixed constant comes from the r plus 1 here that we have to add to make it non-trivial. And then, so the result about the maximum slope, if you apply the usual results in this setting, telling you how the maximum slope behaves for symmetric powers and so forth, is that so that when you compute the degree and let m goes to infinity, then you get exactly this statement here. Okay, so this can be seen as if you want application of the consequence of the positivity of direct images. Now let's move on and then discuss a few things about the foliations. So those are objects inside a tangent, stable with a bracket, and such that the quotient here is torsion free. And then we say that it's, well, algebraic is a very unhappy terminology, but anyway, let's keep it like this for the next half an hour. If this is generically the fiber of some meromorphic map from X to Y, so this is exactly the relative tangent. Now, X itself may be just a Kaehler or a complex manifold, so algebraic is kind of idiotic, but sorry. Now, so of course, given that this is torsion-free, right? Because it's a subsheet in the tangent, is the restriction to some big open set is vector bundle of rank R, say. And then by the integrability condition that you have here, you can write it locally as the kernel of a submersion, but only where you can, that is to say, outside the bed loci, right? So outside the singularities of f, that is to say, where this f is not honest vector bundle, you can always write it as like the fiber of some submersion, like this. And then yeah, so that the fibers of this map corresponds to the local leaves of the foliation, right? That's Frobenius. And then so well, then what we can do is even if this is an open manifold, we can construct a locally finite covering of X0 with such subsets, and then consider the products inside X cross X. Okay, this would be omega tilde. And then, so now inside omega tilde, we have couples Z and W, right, which project map to the same point. So the geometrically, this simply means that W belongs to the leaf passing through Z. Okay, we can talk about that leaf passing through Z because again, we are at points where this is vector bounded, right? Now this lambda here, consisting of such couples, it's what it can, just a locally closed analytic set of dimension n plus r, which in general is not the restriction of a closed analytic set inside X cross X. As a matter of fact, if we look at the Zariski closure, the smallest analytic set containing this lambda, well, of course, it will contain X0, right, embedded as diagonally here. But then a simple remark is that the foliation is algebraic if and only if the dimension of this V is the same as the dimension of the lambda, that is to say n plus r, okay? So if we are able to show that for this weirdly constructed lambda, the Zariski closure has the dimension n plus r, then we are done with the algebraicity, okay? So this is a simple remark, nothing to explain about it. But then, yeah, so that's what I said. So this sort of construction, it was used probably well, first time I saw it was in a paper by Bogomolov and McQuillan long ago. They did this along a curve, but then it makes sense to do it in general for like this, like I just presented. And then now, let's move on to the following, let's say, win-win result, which is the following, which was, like I said, versions of it by Bogomolov and McQuillan long ago, then Jean-Benoit Bost, who will appear a bit later again, and Frederic Campana and myself. Now, the version which is here is due to Stéphane Druel, who should be here as well. Sorry about that. Now, what is why is the win-win result? Well, because if we have a projective manifold and a holomorphic foliation, then let's assume that F is not algebraic. Then we know that O of 1 is pseudo-effective. Okay, so if you take a desingularization of this sheaf F, then you have O of 1, and then this line boundary is pseudo-effective here. Okay, so win-win, because if is algebraic, then let's say from some point of view you are happy because the leaves are not wild and then move around like you cannot control. But then if this is not happening, you still have something, you have the positivity of O of 1. And you will see that the explanation is very simple. So the dual is pseudo-effective, say, in the language I mentioned before. So now let's assume that, just for the sake of the argument, that the desingularization is the sheaf itself. Let's say that we don't have any troubles with the singularities of F. I mean, I want to say from the very beginning that this is one of the very rare instances where the singularities of a foliation, they don't create any particularly difficult problems. In any other problems I know, this is a very, very, very severe difficulty in dealing with the singularities of foliation, but not here, strangely enough. Fine, so then let's take an ample line bundle, and then for each couple of parameters, m and k, let's look at this space of sections, the symmetric power of the f tilde, f star, the dual of f, twisted with a to the k. And then two things can happen. Let's say that there is some epsilon positive such that this space of section is vanishing as soon as the ratio between m and k is bigger than epsilon 0. Now, if this is happening, then what's the upshot? Then you can do a very simple calculation and then deduce that actually the growth of the space of sections here for a to the k restricted to v is precisely this, k to the power n plus r. So, which means in particular that the dimension of this, and so again, v was the Zariski closure of the set we constructed associated to the foliation. So the dimension of v is the right one, so it follows that f is algebraic. But then if this is not happening, then epsilon 0 against of what sometimes is believed, we can take it bigger and bigger. And then the conclusion here is that f is algebraic. So you can the dual is pseudo effective because you have sections which are non-zero when m divided by k goes to infinity, so to speak. Okay, so you can produce sections with almost without the help of a, which means pseudo effectivity. Okay, so that's what it is. Now, application of this method. Let's say that the minimal slope of f is positive. What I want to convince you next is that this condition ensures that f is algebraic. So why is that? Now let's consider a section in this symmetric power of the dual of f twisted with a to the power k. Now the maximal slope of this is positive because of the existence of this section. And then on the other hand, it's k times the slope of a minus m times the minimal slope of f. Now, since this minimal slope is positive by our assumption, this bounds the ratio here for which you will have a non-zero section. Okay, so that you are in this situation, in this context. Okay. Now here, because we are at this point, and because you are so nice to listen to my talk, I must confess that I don't have any really serious intuition about this. If you think, I mean, why this works, in the sense that if you know that all the quotients of f have a positive degree against some Gaudish geometric, then necessarily the leaves of f are closed. The only vague explanation that one can imagine is from differential geometry. When you have a complete Riemannian manifold for which Ricci is strictly positive, it's greater than some multiple of the metric, then you know that it's automatically compact. Okay, that's a very old result by Mias. So somehow, very vaguely, the only explanation of this, the fact that the leaves compactify, is maybe some similar phenomenon, but it's very, very super vague. Anyway, nevertheless, it's true. Now, yeah, so like I said, f is algebraic if this minimal slope is positive here. So, but then as you can see here, we really used a lot the fact that we are in a projective setting. That is to say, we have an ample line bundle at hand, and then the dimension of v was computed by looking at the growth of the space of sections, which doesn't leave much hope for the Kaehler case until Wu came along, and then he obtained the following result. And then so basically the same thing works in the compact Keller situation. Okay, so like I said, it was the result obtained by Wenkao 1 year ago, and then I generously put Junyan here and myself because we got a much simpler argument. Now, so somehow, what is how come that one can get rid of the ample line bundle? Now, the observation is that the result of both his algebraicity result I mentioned before is possible to implement him in the current context. That's somehow what happens here in this reference. So let's assume that for the sake of the argument that f is non-singular, and remember the context as x is inside the diagonally embedded in the product, and here the lambda was consisting in the local leaves of the foliation, and v was the Zariski closure of this inside the product, analytic Zariski closure. Now let's assume that is not algebraic. Okay, the dimension of v is at least n plus r plus 1. Then what is happening? So if we fix a Keller metric on this product, now in the first place, it is enough to construct a sequence of closed positive currents with logarithmic poles and fixed cohomology class in, let's say, in this omega, such that the restriction of this sequence tk to lambda here at the generic point of x tends to infinity. Okay, so here this is a very okay. So maybe let me first explain why it's enough to do that. Because if we blow up the diagonal x, what will happen with this sequence of currents? The inverse image of tk restricted to this lambda minus the multiplicity that you get here times the exceptional divisor restricted to d will be pseudo-effective. But then O of 1, it's exactly O of minus d restricted to d. And then here, this class is fixed, so to speak. And this one goes to infinity. So this is why you get the pseudo-effectivity of O of 1. But then here, this is far easier to say than really to do it, to construct this sequence of currents, because, and then it's really specific to the fact that this lambda here is transcendental. The Zariski closure is, the dimension of that is strictly bigger than the dimension of lambda, okay? If lambda would be a compact manifold, this is ridiculously wrong. Okay, it's because the long numbers are controlled by the cohomology of this object, but here we don't have any cohomology because this is not compact. Okay, so this is what allows to somehow this is what is exploited. The non-algebraicity of this reflects into the fact that we can construct such objects. Okay, and then now the existence of the currents is established by using the Monge-Ampère equations. So the concentration of mass method. This is a method which was invented by Jean-Pierre de Mailly, so in connection to the Fujita conjecture. And somehow, if you look in the literature, it's very often used as a substitute when we don't have any ample line boundary. I'll not discuss this here, just mention other applications of this method, that is to say, constructing singular objects by using analysis. If you want, this concentration of mass is there is the analog in algebraic geometry would be that you have some big line boundary and you fix a point. then you can construct a very singular divisor at that point, and the magnitude of the singularity has something to do with the volume of the divisor, right? So that's the Monge-Ampère theory allows you to do that even if you don't have you only have a 1-1 class, you don't have any space of sections to count how many do you have, how many you can vanish, and so forth. Well, anyway, so and this somehow, even the bounds for the Fujita conjecture in Jean-Pierre's paper were rather far from the expectations. The method that he invented there was used many times, and other applications like positive to direct images or characterization of the Kaehler cone and so forth. So somehow, so what is to be remembered is that the same statement holds in the Kaehler case, and then it goes by constructing these objects by using Monge-Ampère theorem. Fine. So now I'm almost at the end. So let's discuss how these things come together to give the proof of the result I was mentioning. So I will start with the second one. So we have a foliation on a compact Kaehler manifold for which the minimal slope is positive. So in the first place, what we want is to show that this is the kernel of some differential of some map, and the fibers of the map are rationally connected. That's our goal here. And then the main steps are as follows. Now, in the first place, if the dual is pseudo-effective, then what is happening? By the results that I mentioned before in connection with the Griffiths conjecture, the maximum slope of the dual will be positive, and then this cannot happen because here we said that the contrary is happening. Fine. So then this one is not pseudo-effective. So by the algebraicity result, the foliation is already algebraic. So we have that map. Now, standard reductions are coming into the picture. That is to say, resolving the indeterminacy and so forth, putting a few things in general position. And then you get a map from X to Y in such a way that generically F is the kernel of the differential and the canonical of this foliation, which makes sense, right? Because after all, this is just a coherent torsion-free sheaf. So then it's the same as the relative canonical of this map minus the discriminant. Very nice. And then if that's the situation, again, that X is not projective, because if X is projective, things are known. But then since X is not projective by Kodaira, we can find a non-identically zero holomorphic 2-0 form. And then again, Hodge theory tells you that actually there is some Kaehler metric for which this omega plus sigma bar is rational. Okay, so it's a rational 2 form. Yeah. Now the claim is that actually this sigma is automatically zero on the fibers of P. So why is that? Well, if not, we have a non-trivial map from the second power of F to OX, and again, this is the quotient of the second exterior power of F. So again, we are using this hypothesis, and then this cannot happen, right? So then it follows that this class here, when you restrict it to the fiber, well, is everything you can dream of is rational and positive. So in the first place, it forces the fiber to be projective. And then the second claim is that the canonical of these fibers cannot be pseudo-effective. Now, why is that? Because if it is, then it follows that by the positivity of direct images term that I mentioned a few minutes ago, it follows that the positivity from each fiber transfers to the relative canonical minus the discriminant. But then we already know that this difference here is exactly the canonical of the foliation. So we will get a positive degree against this gamma, and then we are done. Okay, so we reach a contradiction. And then, so the fibers are projective, canonical is not pseudo-effective, so then these fibers are uniruled. And then now from uniruled to rationally connected, there's of course a gap, but then you consider here the proof is really standard. You look at the relative minimal rational vibration for the P. And then the fibers, you deduce that the fibers are rationally connected. Okay, so these are somehow the steps of the proof. All right, let's see now for the quotient of holomorphic tensors, and with this I'm done. So now we know that the canonical is pseudo-effective, and we have a quotient here. And what is our goal is to show that the determinant of this quotient is pseudo-effective. Well, so if it doesn't hold, if this one is not, then necessarily the degree of this quotient with respect to some movable class, for example, with respect to some Gaudish metric here, has to be negative, right? Now, if it is happening like that, then this means that the maximum slope of the tangent is strictly positive. So then now stability theory works perfectly well with respect to Gaudish metrics, and it will tell you that actually there is a maximum destabilizing subshift F inside Tx. And then given that this is a maximum destabilizing, then it's necessarily stable with respect to this class, gamma. And by the positivity of the degree of F here, it follows that the minimal slope with respect to gamma is positive. And then now we're in good position to apply the previous result, except that we don't know yet that F is a foliation, but then Miyaoka helps us again, saying that if we look at this map, this must be zero. This must vanish, and then you get this by evaluating degrees against gamma here. All right, so F is a foliation with positive minimal slope, so it must be algebraic. So has compact and rationally connected leaves. But then this, of course, cannot happen because the canonical is pseudo-effective, right? So you cannot be pseudo-effective and rationally connected. And then this is all I wanted to say, and thank you very much for your attention. Okay, thank you.
Thanks so much. Questions from
say something. Thank you.
Any questions?
May I ask if there's a way to put a singular Hermitian metric with positive curvature on a log canonical pair?
Could you detail a little bit the question? What do you mean exactly?
For example, assume we have a simple normal crossing pair XD, and the coefficient of D could be 1.
Yes.
We know that if it's a KLT thing, then we can put a kind of some canonical singular Hermitian metric on it with positive curvature and minimal extension property. And I'm wondering if there's an extension of this result to a log canonical case.
To the log canonical case, I think that what you can do is to somehow, let's say that you have only one component with coefficient 1, and the rest of them are normal, strictly smaller than 1. And then what you can do is somehow to look at this residue map, right? So you look at from your low canonical pair, you restrict to the coefficient 1, and then you have a kernel. So then in this way you can construct a metric, but I mean from the two pieces, right? To the left because there is no coefficient 1 anymore, and to the right because you can prove that the image of the residue map has some positivity. Okay, so somehow it's not a direct metric that you can get as nice as in the log terminal or when you have coefficients smaller than 1. But then you still have some positivity from both sides. Okay, that's the best I can say.
Okay, thank you.
I have a maybe vague question. So if you have a compact Kaehler manifold and take some polarization, I mean, I don't know, maybe movable polarization or Kaehler class, and then look at the tangent bundle and the Harden-Racine filtration with respect to that, and assume that, I don't know, the maximum slope is positive. Can you say does your result say something about like when you put together all the pieces of the Harden-Racine with, say, positive slope?
Maybe.
Do you get a foliation? Does it say something about the reefs?
Maybe. I don't know. But yeah, it's likely.
So without assuming a priori stuff about KX, but
yeah. Sorry, it's likely, but let's discuss it at the Oberwolfach.
Okay, sure, thanks.
So maybe a small question. So it sounds like in the end you are using tensor product of this cotangent bundle, and the maximal slope is just the sum of like a multiple of the factors. So I mean, so are you using is this proof using the Hermitian-Einstein matrix?
No,
and so forth,
no,
or
it's just the
or is there a
property of
direct proof in the Kaehler case as well?
Unfortunately not. You just use the properties of the slopes, the maximum slope, like behaves additively and so forth.
Right. So basically my question is that, so in the projective case,
oh yes, no,
to prove that tensor product preserves semi-stability requires some argument, right? So
absolutely, yeah. You're right. Here is the corresponding result holds. You need this Hermite-Einstein metric to prove the result, which is known to exist.
Okay.
Thank you. I misunderstood the question, but you're right.
Yeah. And then maybe like a slightly off topic but related to this question. So in the projective case, of course, there's a different proof for proving the tensor product, this additivity formula for the maximal slope by restriction theorem. Is there some analytic version of this restriction theorem?
Not that I know. I mean that's usually the trouble. All the results that many results in projective setting are proved by restriction to generic complete intersections. But then there is nothing, no analog technique in the Kaehler world. For example, when you look at the Bogomolov-Giesecke inequality in the projective setting, you can argue by taking complete intersections and then reduce to the case of surfaces, and then, for example, even if the initial manifold is log terminal, for example, then this surface would have the same type of singularity, and then you can argue with that. But then in the Kaehler case, there is nothing that exist that would do the job to allow you to restrict. Probably the closest I know is this is beautiful result by Donaldson saying about the existence of the symplectic submanifolds. But then those are almost algebraic. They are not algebraic. They are just symplectic. So that's nobody ever did something with that. Yeah.
Mm-hmm. I see. Okay. Yeah,
So yeah, I guess you know the result, right? So you have let's say omega. Omega is in particular a symplectic form, and then you can construct these hypersurfaces, for which the tangent boundary is very close of the holomorphic tangent boundary at every point. So it's very tempting to say that, okay, those would be my hyperplane sections, but then yeah, no.
Mm-hmm. Yeah, thanks.
Thank you.
Any other questions for Mihai? Okay, so if not, thanks again. So,
Well, thank you.
very cool talk.